Okay, let's kind of get back to what we were talking about yesterday. We were looking at functions, right? We talked about relations. We defined what a domain and a range are, and then we specified what a function is, right? Special kind of relation. What's our easy definition of a function? For each input, exactly one output. Okay, good. That's really our definition of a function. Special relation where we get one output for each input. All right, so we did some stuff yesterday. We looked at this stuff called function notation. If we write something like y equals f of x, then this means that x is the input and f is the function that we're defining, right? Y is a function of x. Now, something I want to add to that we didn't really get to yesterday. So the letter x we know represents the input value or the independent variable, okay? The letter y, or f of x, right? Y and f of x are interchangeable here. Those represent the output value, which we sometimes call the dependent variable. Now let's just latch onto those new terms, independent and dependent. It's easy to remember that independent goes with input because they both start with in, right? But they make sense too. If we go back and we look at something like, for example, the volume function that we looked at yesterday, right? So what's the input variable here if we're talking about volume of a sphere of radius r? What's the input variable? That's got to be that one, right? So what is that? R for radius, right? So that's the input, and then we're calculating a volume based on the input variable. So the output variable is V. What does it mean to be dependent versus independent? Just if we're thinking about just the meanings of those words. Independent. Okay, independent means you stand alone, right? Don't need any. Oh, okay, dependent means you need something else. You rely on other people, or in this case, the function's going to rely on an input value, right? So does it make sense then that the radius is the independent variable, because that's the thing that the radius is what it is. But then the volume depends on what the radius is, because we have to do a calculation based on the radius to find the volume. Does that make sense? Okay. So just a little new terminology. So then, for example, we could do something like we could use function notation to build a function that outputs the number of days in a month. We input the month and it outputs the number of days, right? So we could say something like, let's let this function f, the rule for that is going to be if we input a month, then we're just going to look on a calendar and see how many days are in that month, and that's what we output, right? So then f of month is the input. For example, if I put in January, we're going to output 31 because there's 31 days in January. Okay, so then we're defining D as the number of days in the month. We're setting that equal to that function which is doing the work, right? Does that make sense? We do that a lot. We'll do things like we'll say, well, one more time down here. So this tells us that the notation D equals f of m reminds us that the number of days D, the output, is built from a function. It depends on whatever month it is, right? And that's what that function tells us. You've seen stuff like this before without ever being really acutely aware of it. You've probably seen a lot of questions like this in Algebra 1. Remember these, where it says, write the equation y equals 2x plus 3 using function notation. Well, what did you do? What did you change there to write that in function notation? The f of x. We just traded the y for an f of x, right? So we're defining y as a function, f of x, right? And then we're saying, okay, well, the rule for the function, the equation or the formula that we're going to follow is just 2x plus 3, right? That's what we input x's to calculate the value of the function, and the meaning of that is y, the y component, right? Okay, and we kind of separate those two tasks. We said, okay, we're defining y, and I think the reason we do this is we're used to just dealing with X and Y coordinates on a graph. So we want to say, okay, there's an X and there's a Y. Well, the Y is built from some kind of function. We can do the same thing with other functions too, and we did something like this yesterday with volume. Let's consider the surface area of a sphere. So we could say something like, let's represent the surface area S as a function of radius. So S equals some function of radius, right? And then what's the function going to be? Well, that's just the formula we have for calculating surface area, which is just 4 times pi times radius squared, gives us surface area for a sphere. So we can separate those things and say we've got some function, some rule that's calculating surface area, and then we're going to set S equal to that, right? But that's kind of an extra step. What we did instead, I want you to just see that there's another way we can do this that's maybe just a little bit tighter. It's a little bit less writing. Why don't we just combine those like we did yesterday? Instead of saying surface area is going to be some function, it's going to be f of r, and then f of r is going to be this, 4 pi r squared, why not just write surface area as a function, right? Which is what we did yesterday. You see how that makes things a little simpler? Notice how you like the color combo here, blue plus yellow makes green, right, if you combine them here? Pretty tricky. So this in a way is what we usually do. And it's a little better, it's what we do in science and engineering. Like in physics, we wouldn't really define, we would just talk about, like, if we want to write it as using function notation, we include the r. If not, we just write s equals 4 pi r squared, right? Just depends which notation you want, but the variable can still be the same, right? Does that make sense? Not a major point, but I just want you to see that even though we do this with y, and f of x, right, when we're talking about equations of lines and things, you know, it's just kind of an artifact of, I think, the fact that we write ordered pairs as x and y, and maybe we start doing this linear algebra before we ever even know about functions, so we're used to y's, so we make that substitution like that. But in the real world, usually we'll just write the function like that, right? So really it would have been like, if we had really been thinking about this from the beginning and kind of planned ahead as mathematicians and didn't want to have all this extra work, we probably could have just said something like, well, y equals 2x plus 3. If we want to write it as a function, just write it as y of x equals 2x plus 3, right? See what I'm saying? That would have been a little easier, wouldn't it? Oh well. Okay, so let's go now, let's look at, we've got this idea of a function. So let's start using them a little bit. What do? Well, we got a little glimpse of that yesterday when we looked at the volume function. And when you explore it, we talked about like blowing up a balloon, right? Didn't we talk about that a little bit? Like, so it gives you a little bit of an insight into why, you know, the behavior of the function is useful to us. We know down here at the beginning when I put in just a little bit of volume, that changes the radius a lot because that first breath blows the balloon up quite a bit. But then up here, when the volume's gotten bigger, adding a little bit of volume up here, the same amount of volume, doesn't scoot the function over to the right very far at all. It doesn't change the radius much at all, right? So a lot of times we'll want to be able to do things like make predictions based on a function. A function acts like a mathematical model for us, right? So that's not doing. So here we've got some function, we've taken some data, and we've fit the data to a polynomial curve, which we'll do a little bit later. We'll do some stuff like that. And we got back this result. The number of cell phones sold in a city is modeled by this function. N stands for number, right? What's X stand for in this case?
How much? How many?
You'd think it would, right? It looks like it's the year, right? It's the number of years after 2005. So here's the number of cell phones, where X represents the number of years after the year 2005. So we want to make a prediction then. Rounded to the nearest phone, how many phones does that predict that city's going to sell in 2017? So what do? What do we do with that? How am I going to find my answer?
Put the years in the X.
Okay, good. We're going to plug a value in for X, right? This is a really important word in math. This is called evaluating a function. I got this new pen. It just works great. Remember how the other one used to always do weird stuff? This one doesn't do that. Oh, the simple pleasures in life. This is nice. So evaluating a function. What does the word value mean?
Amount?
It's an amount or a number, right? So when we say the word evaluate, that means we're numberizing, right? We're plugging a number in for the variable and seeing what number that produces, right? We're plugging numbers in. We're plugging values in, right? So I'm going to have to plug in what number here? If X stands for the number of years after 2005, and we're interested in the year 2017, what number would that be? What's it going to be? How'd you get that?
Just add from 2005 to 2007.
Okay, so you just figured out what you'd have to add to that. You could also just subtract 2005 from 2017. Everybody agree? So this is going to correspond to X equals 12, right? And that's the number I'm going to plug in. Okay, that's kind of an ugly polynomial. It's got lots of decimals. We don't really want to do that by hand, right? So we'll do this using technology. So I'm going to show you a couple ways you can do this with technology. So I'll show you Desmos first. That's the easiest way. Right here, okay? So with Desmos, I could just go over and plug in the function. Notice what I input there. I just typed in literally this, n of x equals the whole function, right? And it does give me a graph. I don't know that the graph is, it gives me a graph, and I could use the graph, but the disadvantage of that is it's a really big function. I mean, if I zoom out, it's a huge function, right? I mean, it's getting, it's pretty hard to use because it's such a big function, okay? So we don't want to do that. We don't need to, though. Yeah, we don't need to. We can instead, we could just ask Desmos, excuse me, to evaluate the function for us. How do you think what would I type in the next line?
X equals,
No, what were you going to say? I think you're onto something.
X equals 12.
Okay, so we want to plug in a value of 12, right? So we could just do n of 12, and there's our answer.
Oh.
See what it did? It evaluated it for us. That's pretty cool.
Does it plug in 12 to every single one of those?
Yep. Yep, it plugs in 12 for every value of x. Because what we did up here is we defined the function in terms of x, right? So this is assigning the value of 12 to x throughout that function, okay? And we get back 27,832.7. So if I round up, that'd be 27,833. If I round to the nearest phone, right? That's the right answer. Okay? Pretty good, huh? Desmos is really easy to use. We could use a graphing calculator for this also, and I'll show you how you do that. There's a way you can do essentially the same thing on a graphing calculator. We would just, on a TI-84, we would just, I guess I'm going to, well, let me do that. So I'm going to enter the function just like I did on Desmos. I can't set n of x equal to it, though. I have to just enter the expression. So I'm going to say 78.6x cubed minus 1120.8 x squared plus 3628.3 x plus 9867.5. Okay? So I enter that and I get something, right? I mean, when I enter that, I get some number back that's meaningless. Okay, but here's what I can do now. I want to store a value, I want to let x equal 12, right? And then evaluate that same expression when x equals 12. So I can do this. I can just plug in, I type in 12, and then see that button down there, store with the arrow? I'm going to store that as x and hit enter. So now it's assigned the value 12 to the variable x. And so if I just go up, one of the nice things about these graphing calculators is you can go up and grab stuff that you've previously used. So I can go up and highlight the expression and hit enter. That means I'm grabbing it. It's pulling it down to the edit bar. And now if I just hit enter, look what it does. Gives me back the answer, right?
So you hit for 12 and then XT and button.
And then this one right here. So let's do the same thing. Like, what if I put in 9 for x? I could take 9, store that as x. I have to hit enter. So now there's my x value, 9. Now I would just go up, if I want to find out, evaluate the function at 9, I just go up to the expression, hit enter to grab it, and then hit enter to plug in 9. And there's what it would be for 9.
Gotcha.
Okay? So there are other ways you can do it on here, but that's a pretty easy way to do it. Okay? You don't even have to worry about the graph, because on this graph we saw was a huge graph, kind of difficult to work with, right? So it'd be better just to not have to depend on making the graph usable. Okay? All right, so does that make sense? I'm recording this, so if you have any, you can go back and look at this again if you forget. Okay, so moving on then. We said this yesterday, right? We can visualize, so a function we can think of as a machine, right? We're inputting values from the domain and it's outputting values into the range. So think of the domain as kind of like a holding area for all the raw materials that we can put into the machine, and the range is like the warehouse where we're putting the finished products, right? And the function is just following the rules that change the input raw materials into the output products, okay? So one of the things we're going to do here is we're going to look at how we can determine what the domains and the ranges are of functions. And the domains are more important, frankly. The range, we don't really oftentimes worry about what the range is, but we do need to worry about what the domain is, because the domain is the set of all the values that we can feed into our machine, right? And just like you wouldn't want to, I don't know anything about ranching, but if you're trying to feed wheat into what would you feed wheat into? A combine or something? Okay. You don't want to accidentally put in some boulders, right? That would be bad, right? So that's not part of the domain for a combine. The domain for a combine is just wheat, right? You don't want to feed it stuff that it's not supposed to get. Same kind of thing with a function. We only can feed the function the values that are allowed for that function, right? So we're going to look at this in 2 steps. We're going to start off easy, where today we're going to practice, I'm going to give you some graphs, and you're just going to determine based on the graph what's the domain and the range. It's real simple. The next step after that, which will come probably next week, will be we're going to determine kind of mathematically, based on the function, what are the values that we could put in without having a graph. Okay? Let's take, even though that's the harder part, and one we're still going to look at later, I want to take just a second and kind of plant the seed of what that's like, and we'll come back to it later, right? So let's think about let's go back to our volume function. We get a lot of mileage out of this volume function here. So if I'm just looking at the equation itself, V equals 4/3 pi r cubed, the domain is going to be the set of all the values of r that I could input, right? There's kind of 2 ways you look at this. We look at this mathematically, are there any values that we couldn't put in there? And then if it's a real world situation like this, like a geometry problem, then what makes sense in terms of the actual problem that you're doing, ignoring the math, right? So what do we mean by what are the mathematically allowed values? This goes back, and we're going to talk about this a lot all year ago. I've mentioned this a couple times already. There's 2 things that you can't do for real numbers, the 2 fundamental no-nos for real numbers. You can't divide by
Negative.
No, you can divide by negative, that's fine. 10 divided by negative 2 is what?
5.
Negative 5, right? Okay, but there's a number you can never divide by.
Zero.
Zero, right? That's one thing. You can't divide by zero. That's undefined, okay? When you divide by zero, it causes an infinite vertical asymptote in the function, and it doesn't, it messes things up. You can't do that. You can't divide by zero. The other thing you can't do, which is going to be a little bit less familiar to you, it'll be real familiar by the end of the year. Remember, that's the one you can't take a square root of what? You can take a square root of, like, a positive number. Square root of 4 is 2. What's the square root of 0?
Nothing.
0, right? Does that make sense? What times what is 0? 0 times itself would give you 0, right? What times itself is 4? 2 words. But what's the square root of negative 4? It's a problem, right? We're going to learn how to do that, but in order to take a square root of a negative number, we have to use a different set of numbers that's outside of the set of real numbers, called the set of imaginary numbers. Bad name. It makes it sound like it's some fairy dust thing, but it's not. But we'll get to that later. You can't do it for real numbers, though, can you? You can't say something times itself is going to give you back a negative result, because the product of any any number by itself has to be positive or 0, doesn't it? Think about it. If I take a negative number, negative times negative is positive. Positive number times itself would also be positive. There's no way to get a negative result, right? So that's the other rule that maybe isn't quite as familiar. We can't take a square root or any even root, it turns out, a 4th root or a 6th root or a 100th root. We can't take any even root of a negative number. So those are the kinds of things we're going to look for. Like, for example, if we had some function f of x equals 2 over x minus 1, for example, okay, that could be a problem. What value of x would cause us to break one of those two rules? I've got an x on the bottom of my fraction this time, right? So is there a value of x that would cause that numerator to equal 0?
Yeah.
What would it be?
1.
1, right? So this would be an example where we would have to say, okay, x cannot equal 1. That's a boulder we don't want in our combine. We got to exclude the value of 1 from the domain, right? Does that make sense? If we look at this one, that doesn't happen, right? The variable here, it's an r instead of an x, but it's not on the bottom of the fraction, so we're safe. There's no value of r that's going to cause us to divide by 0 there, because the r is not in the bottom, right? There's no square roots in this, or even roots in this problem, so we don't even have to worry about the other one. So mathematically, we're fine. Mathematically, the domain would be all real numbers, right? All real numbers we could plug in for r. What about in terms of physically, though? If we're talking about a volume of a sphere, aka a balloon, what numbers wouldn't make any physical sense? I mean, if the balloon were completely deflated, what would its radius be?
0.
0. But as I blow air into the balloon, what happens to the radius? It expands, and I get positive values for the radius.
You can go the opposite direction.
I couldn't. Yeah, what would a negative radius look like? That doesn't make any sense, right? So even though mathematically we'd say that anything's fair game, physically negative values don't make sense. So we'd have to say that our domain would be all values of r greater than or equal to 0, right? That would be our domain. Okay? Does that make sense? That's where we're going to go with this, like, next week, right? But for now, we're not going to worry so much about that. We're just going to look instead at how we can define a domain and a range just from a graph. Well, one thing we do have to cover, though, is how do we communicate what the domain and the range are? Obviously, one way we can do it, and I just did it, is, here I go back again, is inequality, right? We could use an inequality to define all the values, because here we've got some lower limit. We want the values above that lower limit. Well, that's tailor-made for an inequality, isn't it? That's what inequalities do. So one way to do it is just as an inequality, and that's going to be pretty natural for you. You're going to need some practice, like with everything, but the idea of using an inequality is pretty simple, right? That's one you've already kind of dealt with in life. For example, we could be a little more specific, and let's say we have a domain that's limited on both ends, right? This would be all the values of x greater than 2 and less than or equal to 6, right? That makes sense to us. If I were to graph that on a number line on the x-axis, if this is the number 2 and that's the number 6, what would my interval look like there of values of x that would be okay? Greater than 2 and less than or equal to 6.
3, 4, 5.
Okay, so it'd be 3, 4, and 5, but really 2.1 would also work, wouldn't it? And 2.0001 would work. Does 2 work?
No.
2 doesn't work, but 6 actually does, doesn't it? So how would I represent that, like with endpoints and remember that stuff?
Will it be an open circle?
Okay, open circle,
To
Close.
close circle.
closed circle. Okay, good. So right, that looks like the graph of the values of the domain that would work, right? Okay, good. So another way we can do this is using set notation. And our textbook does a lot of stuff, but I'm not even going to touch it. The pattern for set notation is just totally repetitive. Set notation is just saying the same thing we just did, but it writes it in set notation using brackets, and then it defines what the variable is out here. Well, big deal. I mean, anybody can do that, right? If you can write it as an inequality, then all you have to do here is plug in the inequality and put an x out front and put it in, I mean, they're the same thing, right? So the one that would be used the most often would be inequalities. And so we're not even going to deal with set notation. I mean, when it comes time for the SBAC test, we'll probably review just a few times, if they ask for set notation, what is it? Well, this is it. But you already will have done this a million times, right? And so that's no big deal. We can just essentially cross that one off. I'm not going to have you do it. That's just busy work to me. Interval notation, though, might be a little different. Okay, that's the other one I want to introduce to you. So interval notation is where we're going to take whatever the lower boundary is and the upper boundary and separate them with a comma. So just like with an inequality, a compound inequality, we want it to be like a number line. We have to have the lesser value on the left and the greater value on the right, like a number line, right? So in this case, the 2 would go on the left and the 6 would go on the right. And then the kind of bracket that we use communicates to us whether or not the endpoint is included. If we use a rounded bracket, a parenthesis, I guess is what you'd say, then that is considered to be exclusive, meaning it's not including the endpoint. So that goes with x is greater than 2. That communicates that kind of a bracket, right? One that's rounded. It would correspond to an open endpoint, right? A squared off bracket corresponds, that's closed. That's going to be inclusive, we'd say. That includes the endpoint, right? There's a really easy way to remember this. Think about this statement. Whenever we're talking about writing or graphing these inequalities, more ink is always required to include an endpoint. So inclusive takes more ink than exclusive. Up here it takes more ink because I have to write the extra line. On the graph it takes more ink because I have to fill in the endpoint. And the bracket takes more ink than the rounded parenthesis, right? So more ink is inclusive, less ink is exclusive. Okay? All right, so now let's practice this a little bit. Okay, so what happens, well, let's look at some examples real quick. So what if we want to say something like x is greater than a, where a is a number? Question?
Can I use about that?
Yeah, go ahead. So x is greater than a, right? Inequality, that's easy, right? We know how to say that. X is greater than a, right? No big deal. Interval notation, it's a little bit weird. Interval notation, so we know that the lower, well, if we graph it, oh, how come those showed up? They weren't supposed to. Okay, well, let me do something. I want to get rid of, I don't like the way they graph this, so I'm going to do this. You know what, I actually could leave them up there, but I want to change one thing about them. That's what I'll do. This will be faster anyway. Oops. There we go. There we go. Okay. So the endpoints, let's just write them in red. They're using, and this is notation you might see like in college. Instead of using circles, they're using the brackets, right? Open or squared off brackets, rounded or squared off brackets, corresponding to the interval notation, right? Which is fine. We're not used to that. We're used to using endpoints. So this would be the one with an open endpoint, right? X is greater than A. Okay, how do we say that using interval notation? Well, if you look at this, the lower boundary, the left boundary is A, so the A has to go on the left. We're using a rounded bracket because there's no equal sign on the inequality, right? But what about this part over here, the infinity? What are we saying there? We're saying that the, go ahead.
It just keeps going.
Just keeps going, right? So the boundaries are A on the left and nothing on the right, meaning infinity, right? Infinity is no place you can ever get to, right? If you think you're there, well, sorry, you still have infinitely far to go, right? So we have to use a rounded bracket, of course, with infinities because a squared bracket would make no sense. That would mean that including infinity, and you could never include infinity because it's always way out there, right? So this is the way that we write X is greater than A using interval notation. A on the left of the parenthesis, or the comma, and on the right to indicate that there's no limit, we put an infinity, right? By the same token, if we're saying X is less than A, well then we've got an open circle there and we're going to the left. Well now A is the right boundary, isn't it? So A has to go on the right side of the comma, and to the left we're going to put a negative infinity, because that's all the way out there forever, right? Does that make sense? If X is greater than or equal to A, then the only difference is now that becomes solid and that becomes a square bracket, right? If X is less than or equal to A, that endpoint becomes solid and that becomes a square bracket. And we already looked at an example, you know, like these other ones down here. I think we looked at something like that, but obviously the only difference with the interval notation here, if X is trapped between a lower and an upper limit, is the square bracket just goes wherever we have an equal to included with our inequality, right? Okay, the one that we haven't talked about yet, though, is what if all real numbers work? So one way we can say this is X is an element of the set of reals. That's kind of a fancy math way of saying it. That's saying X is an element of, that's what that thing says right there, is an element of or is included in, same thing, element of the set of real numbers. And that's just what that script R means, is all real numbers, right? So how do we say that using the notation we've been talking about? Inequality notation or interval notation, this new stuff we're looking at, this interval notation. How do you think we would say something like that, that all real numbers are fair game as an inequality? X is greater than and less than. What's going to go on the left side? No, not in this case. So R is one that later on I'll let you guys write it like this. It's shorter. But for now I'm not going to let you. For now we have to use either inequality notation or interval notation. So if I have to write this as an inequality, can I put a number there? If all real numbers are okay, like if I put -1 million, it says X is greater than -1 million, well it also should, -2 million should also work, right? So that's limiting me, and I should be unlimited. So what was the way that I said there's no limit? It's greater than negative infinity and less than
Positive infinity?
Yeah, right? What that means is, that's a weird thing to write, but that's our way of saying there's no limits. X is unlimited. How would we say that using interval notation? What do you think?
Oh,
Like the deal with the slash and then
yeah.
Okay, so
Negative.
negative infinity to infinity is our interval notation way of saying unlimited, right? Okay, so now let's look at a few of these. So let's find the domains for some functions. I'm giving you the graph. Let's find the domain. Okay, so first of all, what's going on with this? I've got some function that runs off the screen, right? Now think about this function. As an ant walks along this, is there any reason to expect that if the ant, as he walks up, it appears to get steeper, right? But there's no limit to how far up the ant could go, right? The plane is infinitely big that he's
Does
walking
it
on.
straighten out, or does it keep curving?
Okay, so it never does straighten out. It never does straighten out. It always ends up going higher and higher and higher. Now, eventually it gets pretty steep, and so one small movement to the right moves him up quite a bit, but it's hard to wrap our brains about this, but there's no limit to how high he can go, right? So even though this is getting steeper and steeper and steeper, he's always going to be making some progress to the right, isn't he? There's no limit. So is the domain, is there any restriction on this domain? No, there's not. He's going to be able to walk as far to the right or the left as he wants to if he's willing to hike really high, right? Infinitely high, okay? So the domain then for this one would be unlimited, right? So how do we write that as an inequality again? X is
Oh,
greater than,
Negative eight.
less than, okay? And as a interval notation, just like that, right? Does that make sense? Okay, while we got this one here, I'm just going to kill two birds with one stone here. Let's look at the range. Okay, range is a set of output values, right? What can you tell me about, now the range is different in this case. If you look at the Y values, they are limited. Is there a lowest or a highest Y value? There is a lowest Y value, isn't there? The ant could step right there and declare, I am on the lowest place on my universe here, right? He can't go any lower than that. What's that Y value? -3, right? So he's going from the point x equals who cares, y equals -3, always up from there, right?
Yeah.
Does that make sense? So if you turn sideways, so you're looking at this, so this is the y-axis, right? Well, that looks like what kind of interval? It looks like one that's greater than or equal to -3, doesn't it? Everybody see that? So does it make sense then that if we want to talk about the range, if I write it as an inequality, I would just be saying y is greater than or equal to -3, right? Everybody see that? Okay, notice I'm using a y, because the range is values of y. If I write that as using interval notation, what would it look like? Oops, sorry, I already messed up. Using interval notation, what would that look like?
The squared up there.
Square brackets?
Y.
Right, but I'm just writing numbers here, right?
Oh, yeah.
So what's the bottom limit for y?
-3.
-3, and there is no upper limit, right? Does that make sense? Okay. How about one like that? Okay, now this is different. This time it does flatten out. It's saying the red line is an asymptote. Okay, an asymptote in math means a line that the function approaches infinitely closely, but it never quite gets to it, right? So if the ant walks backwards along this function infinitely far, he's going to always get closer and closer and closer to that line. Just like, remember the example we talked about, every second, if I take a step towards the door, right, what's the limit of my motion? The point that I'm always approaching? The door, right? Is there any point in between me and the door that I won't ever step on? No, right? I'll step on, there's no dot of ink I could ever make on the floor, as long as it's not on the door itself, that I wouldn't eventually step on, but I never quite get to the door, right? Get the idea? But it looks like in this, as he moves up this thing, there is no vertical asymptote. He's always going to continue to move to the right, okay? So what's the domain of this guy then? Is an inequality first. X is, is it limited? The x values are not limited, are they? He can go infinitely far to the left and continue moving to the right forever. Agreed? So, once again, I just get that stuff, right? Okay? What about the range? Okay, the range is limited though, isn't it? Okay. What's the lower limit of the range? Because it looks like he can go up forever, can't he? Right, so we know that we're going to have y is less than positive infinity. But what goes on the other side?
I have no idea.
Well, what's the lowest the ant can go
-1.
on? -1. Does he ever actually get to -1?
No.
So how would we write that?
Open circle.
Okay, so that's going to be an open circle. Like if I were to graph this thing, if I were to graph the range, it would look like this. He never quite gets down to -1, but he goes up forever, right? So what kind of inequality sign do I have to put here?
One without a line underneath it.
Okay, good. Greater than -1. Everybody agree? Written in interval notation. Does that make sense?
-1 infinity.
Right? Okay. How about something like that?
Oof.
Okay. Now, this time, to think about that, what's the domain going to be? If I were to graph the domain, like on the x-axis, so we're talking about just horizontal motion here, where's the left endpoint horizontally? At 3, right? So we're going to put an open circle there, right? Because you can't step on x equals 3. And then the upper endpoint horizontally is going to be up here
Close.
at 9 with a closed circle. Good. So that's our domain, isn't it? Right? So the domain looks like x is, you tell me, is
3.
what 3 though?
Positive.
No, you're right, but x is greater than
Oh.
3 and
Less than or equal to.
less than or equal to 9. Okay? Written in interval notation. What kind of parentheses here?
Like a rounded
Rounded
bracket.
bracket. Right? Okay, what about the domain? Let's look at the domain. Now let's think about the graph of the domain. What's the lowest value the ant can stand on?
-7.
And can he actually stand on that point?
One of them.
He can, can't he? Right there. He can get down to -7 and actually stand on it, so it's closed, right? What's the highest point the ant can stand on?
-4.
-4, and he actually can stand there, can't he?
Yep.
Right? So that's my range, isn't it? Right? So then, so we'd say y is greater than or equal to -7, less than or equal to -4. Everybody agree?
Yep.
Okay, you got a pretty good start on this. So you could actually you can work your way up through quite a bit. Assignment 2 and then assignment 3, you can do about half of it. You can get a jump on it. Okay?